Hello. In this video, we're going to look at vectors, and we're going to check out how to list them and how we distinguish them from scalars. So a vector is essentially a quantity with both length or magnitude and direction. We've looked at angles in this course, and that's going to give us direction. We've also looked at lengths of triangles. That's going to give us a distance or a magnitude. The first thing we need to do is figure out the distinction between a scalar quantity, which is just a length or a magnitude, and a vector quantity, which is both. One way we represent these vectors would be in boldface. That's going to distinguish them from a scalar. When you don't have the convenience of using boldface, for instance, you're writing it on a test or on your paper, then you can put an arrow over that vector. This table below represents the difference between scalars and vectors. So for instance, you see that bold V is a vector. It represents a vector. That V with a arrow over it represents a vector. We can also have a directed segment, like AB representing a vector, X, just lowercase, not bolded. That's going to be a scalar quantity, a number. V with absolute values, that's also going to be a scalar. We call that the magnitude of a vector. So when we have a vector, we put absolute values around it. We're just looking for the magnitude and no direction. Let's go ahead and check out a few examples here of vectors and non-vectors. So when we're looking at these, we have the wind speed is 12 miles per hour northwest. This is a vector quantity because it lists not only a speed, which would be the magnitude, but a direction, northeast. The temperature is 31 degrees Fahrenheit. Well, this one would be a scalar quantity because we don't have any direction for that temperature. You could argue that it could be negative or positive, but we'll just call it a scalar here. A car is traveling at 75 miles per hour. Even though this does represent speed, there's no direction there. So the speed, the velocity is a scalar in this case. You are biking 20 miles per hour west. Now we have a direction. This will be a vector quantity. And the summit is 12,240 feet. Again, you could argue above and below sea level, but most likely this would be a scalar quantity. And finally, a force of 200 newtons is applied horizontally. Well, applying it horizontally gives it a vector quantity, a vector field. If we want to represent these, we can via drawing them in standard position with our coordinate system. So for instance, number one, my vector quantity there could look like this. The wind speed is 12 miles per hour north and east. So north would be straight up the y-axis, left is west, so east would be right. Here would be our vector quantity right here. So that would be at a 45-degree angle in standard position, and we would call that, since it's a wind speed, maybe W with a line over it. That's how we would represent our vector. Number four, you are biking 20 miles per hour west. So in this case, we're going to be going straight left. That's going to be west, or westerly direction. And maybe I'll illustrate it with a different color. So this vector is going to be going this way, and we could call it something like V for velocity. All right. And a force is applied of 200 newtons is applied horizontally. So this is also a vector quantity, number six. It doesn't really tell us which way horizontally it's applied, so we can actually choose direction here. Again, I'm going to signify it in a different color. So we'll just say the force is applied to the right. And so that's what the vector would look like. It could be going in the other direction. We would need more information. But the thing to notice that when we compare 4 and 6, they're going in sort of opposite directions. So those wouldn't be equal in a way. That's what we're going to be talking about next. Okay, when we're looking for vectors and some properties of them, we have to define the zero vector. This zero vector is going to be represented by just a dot at the origin. And we need that vector because it's going to give us properties when we look at operations with vectors such as addition, subtraction, multiplication, etc. We want to look at equality of vectors. So two vectors are said to be equal if they have the equal magnitudes and directions. For instance, if I have a vector here that's going straight to the right, and I have another vector, but somehow it's located down here, also going straight to the right, as long as those have the same magnitude and same direction, I can slide vectors up and down, left and right. I just can't turn them or flip them or rotate them, but I can slide them to be the same. So in this case, we would say that vector u is equal to vector v because they have the same length and direction. For instance, we could say that the magnitude of u is going to be 3, and the magnitude of v is going to be 3. So those are scalar quantities representing the magnitude, but they both go in the same direction. Okay. We want to talk about adding and subtracting these vectors together. We're going to be looking at this in a couple different ways, but for now, we're going to be looking at this graphically. So when we add vectors together, we can do it in two different ways. We can do what we call the tail to tip method, or we could do the parallelogram method. Below, we're sort of representing the tail to tip method. So one way to represent the addition of vectors is we slide the vector, either one, in fact. So if I'm doing u plus v here, technically, I should go ahead and slide this vector v. So the tail of v is on the head of u. When I do that, I get this illustration to the right, and then I can add u plus v, and the sum will be from the tail of u to the tip of v. We can also do this using a parallelogram method, and excuse me, that's going to be illustrated this way. Let me clear this out. So the parallelogram method takes those vectors and they slide the tails together and they create a parallelogram by replicating those vectors on the opposite sides of the parallelogram. When we go from where they join at the tails to the top of the parallelogram, that will be our addition of those two vectors. Two different ways to look at this graphically. We want to talk about vector components. Vectors have components, and we look at their cardinal directions. In this case, in this class, we're going to be looking at just X and Y directions, but you can look at X, Y, and Z directions. And if you go into calculus, you'll do that. You can also look at totally different directions. We can look at four-dimensional directions by thinking of one variable as time, or we can think of all those variables as different things, but it becomes hard to visualize. Let's keep it simple. So vector components are going to be the lengths of the vector. So it's going to be a scalar quantity in each direction. We can really get this from the angle that they create with the in standard position. So I'm going to be looking at this angle here, theta, from the horizontal of this vector v. If I want to find v sub x, the horizontal direction, I have a trig ratio for that. So v sub x is going to be a vector, v is going to be a vector, and v sub y is going to be a vector. So if I looked at the cosine of theta, that's going to be equal to the magnitude of v sub x, the adjacent, over the magnitude of that vector in general, the hypotenuse. So if I wanted to find v sub x, I just multiply by the magnitude of v, and we get the horizontal component. Similarly, if I take the sine of that angle theta, which is sort of given by our angle in standard position there, that's going to be the opposite side, the magnitude of the opposite side, v sub y, over the magnitude of the vector. And so I could say, multiplying by v, the magnitude of v, that the vertical component is going to be magnitude of v times sine of theta. Now notice how they have absolute values around the cosine and the sine below. If this angle terminated in a different quadrant, then it's a possibility that we would have negative values for the cosine and sine, and we don't really want that because magnitude has to be at least non-negative. So we can go ahead and put those absolute values around the sine and the cosine. As long as we're in quadrant 1, we're okay. So these will be the components of that vector. Finally, we are going to look at the length of the vector. So length of the vector, we can just use that Pythagorean theorem. We can say that the magnitude of v is equal to the square root of the magnitude of the horizontal component squared plus the vertical component squared. A lot of things we've already done help us with these vectors. I'm going to stop this video now and make another one to look at some examples coming up. Thank you.